Hi everyone, this is Tunir and we are the Problem Solving Club. This week's problem is, it's a Newton's Laws of Motion chapter problem. The problem is, okay, we have a block of mass on a floor and the floor has coefficient of friction equaling mu. The problem is, you have to apply a force to the block of mass and move it. Now, you have to move it using minimum force. In which direction would you want to apply the force so that the force required to just move the block, just marginally move the block is okay. The problem is just a mechanics problem. We have a block of mass on a floor. That's the floor. That's the block of mass. There's a mass m. The floor has a coefficient of friction equaling mu. It's a number between 0 and 1. And we have to apply a force to the mass to move it. And the question is, in what direction do we need to apply the force such that the force required to move the mass is minimum? So let's say we apply a force which has an angle theta with respect to the horizontal. We'll consider theta to be less than pi by 2 and more than minus pi by 2, because if it shifts in that direction, it's just a symmetric part. So we won't. It's just the same thing. We don't need to consider theta more than pi by 2. Now the first step is to draw a free body diagram of the mass. So we have the mass here, m. There are quite a lot of forces on the mass. First of all, we have got mg, the gravitational force. Then we've got the normal force due to the reaction force of the floor. I'll call that n. Then we've got F. That's the applied force, the one that we're applying at an angle theta. Then we've got a frictional force. I'll call that F small f. I break capital F in components, F cosine of theta and F sine of theta. Now we write an equation in the y coordinate. We know since the box is not moving anywhere as of now, and it's never going to move in the y-axis. It's not flying up. It's not going inside the ground. So we can write this equation in the y coordinate, that the force along the y coordinate adds up to 0. So n plus f sine theta minus mg is a 0. That allows us to get an expression for n equaling mg minus f sine theta. We'll call that equation 1 theta. And also in the y-axis, in the x-axis, we have an equation. So the box is not moving yet. Then we can write f cosine of theta minus f of friction is 0. Then we have f of friction is just f cosine theta. And here's something we know. We know that ff has to be always smaller than or equal to mu times the normal force. That's the law of friction. That means that f cosine theta has to be smaller than mu times n. When the box is just on the verge of moving, this inequality will turn into an equality, and f cosine theta will become mu times n, and then we have the equation f cosine theta equals mu times mg minus f sine theta, and from there we can write f as a function of theta. In fact, we have f equals mu mg by cosine of theta plus mu sine theta. Okay, now all we need to do is we can actually plot f with respect to theta. You know, as theta changes, f changes, and we need to find the theta at which f happens to be minimum. So all we do is just differentiate f with respect to theta. That's a strategy, and we find at which place df d theta happens to be a 0. So here we go. Right, df d theta is mu mg minus of cos theta plus mu sine theta squared. Then we have minus sine theta plus mu cos theta equaling 0, which means this, whatever happens to this part, we don't care. This part is 0, which means that mu happens to be tan theta. So we get the angle. The angle at which the required force is minimum is tan inverse of mu, which also is known as the angle of repose. Now we've made an assumption. The assumption is that this extremum happens to be a minimum. We can prove that later, or that's sort of obvious. Now we want to calculate the force at this point. The force happens to be, now the expression for force was mu mg by cosine theta plus mu sine theta. With a little math, we can find out that this turns out to be mu mg by 1 plus mu squared, and voila, we have the formula for the minimum force, F min mu squared by mu squared. You see, this force is less than both the forces that's required to lift the box. If you want to lift it, you want the force mg. This happens to be less than mg. If you want to push it extremely, like exactly to the right, you need a force mu mg, because you need to beat the friction. So there you go. So you need mu mg. That's less than mu mg also. So that's the minimum force required to move the box, and that's the angle at which the force is required to be applied at. That's it. Thank you.